Hello everyone, my name is Gibson Carter. I will be presenting on our research, intermediate task, transfer learning, leverage sarcasm detection for stance detection. My co-author is Dr. Susan Koch from the University of Arkansas in the United States of America. About me, I received a master's degree in computer science from the University of Arkansas in 2022. Currently, I am a doctoral student in computer science in the university. I joined in spring 2023, and I'm also working as a graduate research assistant in the electrical engineering and computer science department under the DAT project, which also sponsored this particular work. My research interest lies in the application of deep learning techniques and pre-trained language models in natural language processing tasks like sentiment analysis, stance detection, and Luma veracity detection on social media. Our presentation is outlined like this. We talk about the motivation, an illustrative example, which is also part of the motivation, our approach, experiments and results, contributions and conclusion, and finally we talk about our future work. Stance detection is defined as the automated identification of an individual stance on a specific topic based solely on the utterance of the person or authored material. Stance labels categorize expressions into three major categories, that is, in favor of the topic, against the topic, or none, meaning that they are not supporting or they are not against. Some other works, they also include a fourth category, which is a query. So it is not basically like a comment, but mostly it's like a question to the topic. Social media platforms provide a vast amount of information on diverse topics, fostering stance detection in social, business, and political applications. So in other words, on Facebook, Twitter, which is now called X, Reddit, and many other social media platforms, people discuss about a lot of things, a lot of topics, whether they're in business topics, political topics, academic things. So those topics are the ones which help a lot in applying stance detection into the information which is discussed and which is gathered from social media platforms. Now, most of the data which is, out of the information which is discussed on social media has some inherent sarcasm. So the inclusion of sarcastic and figurative language in posts drastically impacts the performance of stance detection models. For example, let's look at the following illustrative example. So we have this comment which is taken from one of the topics which has been widely discussed on Twitter, feminist movement. So the comment reads like, I like girls, they just need to know their place. So if someone can look at the first part of this sentence, it is more positive. Even the following part, it carries a positive connotation since it is like using positive words. So in that way, it's very easy for a human, like a human being, if you can read that sentence like 2 times, can easily know that I think this topic, this comment is against for the feminist movement thing. While it will be very hard for a stance detection model, which is learning in a machine, a computer, to detect the stance which is portrayed in this particular comment. So in this way, we need firstly to infuse some sarcasm knowledge into the stance detection models before we use them for the target task of stance detection. So this this nature of sarcasm in these comments is one of the main reasons why we have chosen to use sarcasm detection to pre-train a model on sarcasm detection before fine-tuning it on the target task of stance detection. So this is how our work has been approached. So the generic name of this work is intermediate task transfer learning. So it has 2 phases. The first phase is pre-training the model on intermediate task. The intermediate task is sarcasm detection, or whereby we just need to learn the model to understand whether a piece of text is sarcastic or it is not sarcastic. And then after we pre-train on this intermediate task, then we have to fine-tune it on the target task, which is stance detection. So here below is how the training pipeline of this work looks like. So the first part is just showing like the components of the underlying model, which we will talk shortly in the following slide. And then the intermediate task. Here, the model is trained on the intermediate task, and then lastly, we fine-tune the model on the target task, stance detection. The underlying model has 3 main components. We have the input layer, which is followed by the embedding layer. So the embedding layer either has belt or rotator. And the embedding layer is followed by an integration of 3 deep neural networks, the convolutional neural network, the bidirectional LSTEM, and a dense layer. Now, this is how we formulate our problem in this particular work. Given a tweet T or a comment T represented as a word sequence which has length L denoting the length, with L denoting the length, the sequence length, then predict its stance regarding a given target. So can be any topic which we need, which we are working on, any topic. Stance labels are categorized as in favor, whereby this label is supporting the topic, against, which is opposing the topic, or none, indicating neutrality towards the target. So this is how the model is looking like. We have the first part is the input layer, which does some transformation to the input, like most of the data preprocessing, case forwarding, text normalization, and other stuff. Now, the output is the input IDs and the input masks, which we feed to the embedding layer, which has either belt or rotator. And then from there we have the encoded comment, which is applied to the convolutional layer, which produces the feature maps, which we feed into the bidirectional LSTM layer, which provides higher level features. And then we use those higher level features to feed into the dense layer. So the dense layer is the one which is used to now to finally differentiate like which is the class now that is associated with this particular input comment. And then lastly we have the soft max layer, so which gives the different probabilities depending on how the dense layer has predicted this particular input comment. Next is the experiment. So since the previous work, nobody has ever done sarcasm detection pre-training for stance detection. So we used 3 different sarcasm detection datasets with different sizes. So our aim here is was like to explore like what kind of attributes and skills does a model learn from an intermediate task and transfer that knowledge to the target task. So that's why we're trying to use different data sets, and these data sets, they are also sourced from different domains. For example, the first one, the first one is from, it's not from necessarily social media data set, it's just from a specific website. The second one is from Reddit, and the last one is from Twitter, X. So it's like the 2 data sets are from social media, second and the last, and the first one is from just a designated website which was used just to crawl this particular data set samples. And for the target task, task detection, we use the 2 common available datasets, the same eval 2016 task dataset, which was used for stance detection competition and was introduced in 2016. And this one has 5 main topics which have been discussed in this particular dataset. 3 of these topics are atheism, feminist movement, and climate change. And this second dataset is multi-perspective consumer health query data, NPCHI. So this dataset also has 5 targets, and in this dataset mostly in the 5 targets they mostly discuss about health related things, issues. And below here we have the experimental settings which we used in this particular experimentation. So these are the results which we have. So the first table on top is the results which we obtained without including sarcasm pre-training in the model. So the aim was like to firstly see how the model will perform before any addition of sarcasm pre-training. So it is shown that our model, which uses BERT down here, outperforms these other models in almost most of the targets here, and it was outperformed by only 2 of these models on only 2 targets, respectively. It was outperformed by Roberta, but our model which used Roberta on the CC, on the climate change target, and by ChatGPT on the Hillary Clinton target. And down here we have results after we included now sarcasm detection pre-training into the model. So we used here only one, we used only our model which uses BERT because it's the one which like gave promising results here. So we just took this model only to use it for sarcasm pre-training. And here it is shown that one of the datasets for sarcasm detection pre-training is the one which gave improvement on this BERT model, and the other 2 datasets did not do anything to this particular model to improve the performance, and they are also outperformed by this BERT model, which is superior in the first table. So there were a lot of observations which we made here. First is it's because of difference in domain, where the target task stance detection datasets, where they are outsourced from, where they are sourced from, and where these pre-training datasets, they're also outsourced from different domains. And also topic coverage was different between these 2 datasets, and also sentence length between these datasets was different between these datasets and the stance detection datasets, which were we use as the target task in this particular work. So those factors are the ones which contributed, like, for these 2 first datasets not to have any improvement in the performance of the model, while this last one had lexical attributes which were similar to the target task of stance detection. So that's why you can see the improved performance here. And this last table is just showing the results of ablation study. So the first 2 parts is on the ablation study we only use again the model which has BERT. So the first 2 are the ones which have sarcasm pre-training, which do not have sarcasm pre-training, and the 1, 2, 3, 4 down here are the ones which have sarcasm pre-training. Only we use the dataset which performed well for pre-training, the ST dataset, And also we removed some of the components on both sarcasm pre-training and without sarcasm pre-training to see what will be the impact of removing a specific component into the generalization of the model. So it can be shown that the model which used all the components, that is sarcasm pre-training, BERT, convolution, biostream, and also a dense layer, is the one which had overall promising performance on the target task. Now contributions and conclusion. In this work, we introduced a transfer learning framework that leverages sarcasm detection for stance detection. The model underwent separate pre-training on 3 sarcasm detection tasks before fine-tuning on 2 target stance detection tasks. We separately fine-tuned Roberta and BERT and sequentially concatenated them with other deep neural networks. So we found that using BERT as the embedding layer gave promising results compared to Roberta. We also established the correlation between sarcasm detection and stance detection through failure analysis. So here it was found that most of the examples which were misclassified were those which had sarcasm in them, and then after we used sarcasm pre-training, most of the sarcastic comments were correctly classified by the model. We also showed that not every sarcasm detection intermediate task improves stance detection because of incongruous linguistic attributes. So in other words here, care has to be taken into consideration when choosing a sarcasm detection pre-training task to be used to improve stance detection, because the attributes of these 2 tasks have to be similar and the same in order for the model to transfer well the sarcasm knowledge from the pre-training task to the target task. To the best of our knowledge, this is the inaugural exploration of sarcasm detection pre-training applied to Roberta or BERT plus convolutional layer plus bidirectional architecture for stance detection fine-tuning. Our future work will assess variant, BERT, or Roberta embeddings tailored to health-related text data. We will also concentrate on cross-target stance detection, and we will do more comprehensive examination of other intermediate tasks, including sentiment and emotion knowledge. So that's all we had for you. Thank you so much for your attention.